Welcome to The Explainer. We're kicking things off today with a massive, mind-bending question. How do you teach a machine to see? I mean, for us, seeing is as natural as breathing, right? But for a computer, a picture is literally just a blank wall of nothingness. So how do we cross that gap? How do we perform this incredible magic trick of turning a blind machine into something that can actively perceive the world around it?
Get ready because we are talking about computer vision-y. You might notice the all caps excitement there, and honestly, the topic completely deserves that kind of hype. Let's dive right into the magic of machine sight. We're looking at a revolutionary field of artificial intelligence that lets computers observe and actually make sense of visual data like images and videos in ways that are totally changing our world.
So here is our roadmap for The Explainer today. We'll start with humans versus computer vision, break down the anatomy of an image, explore how neural networks see, look at real-world computer vision, map out the AI project cycle, and finish up with ethics in AI. Let's get into it. Starting with Section 1, humans versus computer vision. You know, when we look at something, it's just light reflecting off an object and entering our biological eyes. Our brain naturally interprets it, and we learn through experience over time. But let's be real, we have limitations. Our judgment is subjective, and our eyes get tired. Computer vision, on the other hand, it uses mathematical algorithms and looks at pixel values. Sure, it requires massive training data sets to learn up front, but the trade-off is huge. It delivers consistent, tireless accuracy. Machines basically bypass our human limitations to offer this microscopic precision 24/7.
Now, a quick clarification, because understanding this difference is key. Computer vision is not the same thing as image processing. Image processing is really just a subset used to tidy up a picture. It's about tweaking the raw image. Think rescaling a photo on your phone, correcting the brightness, or shifting the tones. Computer vision is the overarching brain that's figuring out what that image actually means. It extracts information to infer meaning and make predictions, like recognizing handwriting or spotting a specific object.
Moving right along to Section 2, the anatomy of an image. It all starts with a tiny square, the pixel. This is the foundation of everything a computer sees. A pixel is just a picture element, literally the absolute smallest unit of info in a digital photograph. They're usually arranged in a flat, two-dimensional grid. So when you hear the word resolution regarding a screen, like a monitor that's 1280 by 1024, it just means we're counting those pixels across and down. 1280 pixels from side to side and 1024 from top to bottom. But how does the computer actually process those pixels? Well, to a machine, a picture isn't a picture at all. It's a massive grid of numbers, and each pixel gets a value. In grayscale images, those values range from 0, which is pure black, all the way to 255, which is pure white. Every shade of gray falls somewhere in between. For colored images, known as RGB images, it's just slightly more complex. They're made of 3 primary colors: red, green, and blue. Each of those colors gets its own numerical value from 0 to 255. By combining those 3 numbers, the computer can represent any color imaginable. Which brings us to Section 3, how neural networks see. Meet the heavyweight champion of this space, the convolutional neural network, or CNN for short. This is a deep learning algorithm designed specifically to take an input image, assign learnable weights and biases to different objects in that image, and successfully differentiate them. It processes all this visual data through several distinct, honestly fascinating layers. The CNN's secret weapon? The kernel. Think of a kernel as a tiny mathematical magnifying glass. It's a matrix, a small grid of numbers that gets slid across the entire image. As it slides, it does element-wise multiplication with the input pixels. This mathematical operation is called convolution. The whole point of sliding this kernel around is to transform the data, enhancing the output to extract very specific features from the image, like hard edges or subtle textures. So imagine sliding that kernel over just a tiny 3x3 patch of pixels. The computer multiplies the pixel values by the kernel values and adds them all up. After crunching that simple arithmetic, the computer might spit out a single value, like -752. And just like that, this single number now represents that entire little piece of the image, holding crucial information about its features. This whole process builds step by step, like an assembly line, through the network's layers. First, the convolution layer extracts features using those kernels to produce a feature map. Next, the ReLU function steps in and removes the negative numbers to make abrupt color changes and edges super obvious. Then the pooling layer shrinks the image's spatial size, making it manageable and way more resistant to distortions.
Finally, the fully connected layer takes those probabilities and confidently yells out a classification label, like, hey, I'm 99% sure that's a cat.
Okay, Section 4, Real-World Computer Vision.
So where is this actually happening? Everywhere. These complex algorithms are seamlessly integrated into our daily routines. Security systems use computer vision for facial recognition. When you throw some goopy dog ears on with a face filter on Snapchat or Instagram, yep, that's an algorithm mapping your facial dynamics. You've got Google's search by image and retail stores tracking customer navigation routes. It's the absolute fundamental technology making self-driving cars a reality. And it's literally saving lives in medical imaging by turning flat 2D scans into interactive 3D models for doctors. Even the Google Translate app uses it to read foreign street signs through a phone's camera in real time. It's wild.
Let's pivot to Section 5, the AI project cycle. You can't just write some code, cross your fingers, and hope for the best. Building these models follows a very deliberate, structured cycle. Step 1 is problem scoping, using the 4 W's, who, what, where, and why, to clearly define the issue you're trying to solve. Step 2 is data acquisition, which means gathering authentic data from surveys, web scraping, sensors, or open source portals. Step 3 is data exploration, where you visualize that data to spot trends. Step 4 is where you actually build the model and select the right algorithm. Step 5 is evaluating the model to ensure it's accurate, which finally leads to Step 6, prediction. This cycle ensures you aren't just throwing math at a wall to see what sticks. You are engineering a deliberate, targeted solution. To put that cycle into perspective, let's look at an amazing real-world use case: coral bleaching. Climate change is causing corals to lose their color and die off, destroying entire reef ecosystems. By following the AI project cycle, researchers acquired a massive dataset of bleached corals, explored the visual patterns, and built a classification model. Detecting that bleaching at an early stage using computer vision can literally help us prevent environmental disasters. And that brings us to our final topic, Section 6, Ethics in AI.
Look, this tech is incredible, but with great power comes some massive risks if left unchecked. Data privacy is a huge one. These systems require a mountain of user data, raising serious risks of mass collection and misuse. Then there's unemployment, as automation inevitably shifts human jobs across multiple industries. We also have to be ultra-vigilant about AI bias. These systems can absolutely inherit the unfair biases of their developers or their training datasets, leading to skewed decisions in critical things like hiring or banking. And finally, AI access. These advanced tools are very expensive, which risks creating a massive divide between those who can afford them and those who can't, worsening global inequality. There's a quote from the source material that really hits the nail on the head regarding our responsibility here. AI tools must be used responsibly to ensure their benefits contribute to society's welfare without causing harm. Because at the end of the day, it's not just about writing the smartest algorithm, it's about deploying it into the real world with a conscience. So, I'm going to leave you with this final thought to chew on as you consider your own role in the future of artificial intelligence. As computer vision becomes even more advanced, how will you ensure fair access and eliminate bias in the AI system shaping our future? The magic of Machine Sight is already here. Now it's up to us to guide exactly what it's looking at. Thanks for joining this explainer. Keep asking the big questions, and we'll catch you next time.